Hi, everybody. Welcome to the last FORCE seminar of the semester. Thanks for joining us today. I'm Kara Bregman, a research scientist here at FORCE. And before we start, I want to remind you that you can see videos of our previous seminars on YouTube. This video should be posted next week, and you can sign up on the listserv on our website to get updates. And we should have a new website coming to you before the end of the year. Also in January is our third winter workshop on recent advances in high-pressure research. You can register for that at the link you see on your screen. This will be virtual only on the mornings of Tuesday and Wednesday, January 14th and 15th. And our abstract deadline is next Friday. So there's a link there in yellow. You can submit your abstract. We're especially looking for more that has to do with IHPV or the torsion press. We're pretty anticipating to be pretty multi-anvil heavy, and we want to make sure that we cover the entire range of apparatuses that we have available in our lab. This workshop is free, and we'll have invited talks by Dan Frost, Fabrice Gaillard, Tomo Katsura, Megumi Kawasaki, and Jorge Cubero-Cecin. All right, without further ado, I will turn it over to Felix. I'll read a short bio here. Felix Marxer received his PhD in 2021 at ETH Zurich and is currently an experimental petrologist and staff scientist at Leibniz University, Hanover. He manages the experimental lab there that includes internally heated pressure vessels, cold seal pressure vessels, and gas mixing furnaces. His current research focus is on arc magmatic systems and phase equilibria. All right, thanks, Felix.
Well, thanks, Kara, for the nice introduction, and especially for having me here today, and also all of you for joining. So since at FORCE you're currently in the state of getting an own internally heated pressure vessel, I thought I'll take this chance now of this talk to first give you a general introduction, how these facilities work, but also show you how we can use them to study crustal magmatism. And therefore, I divided this talk in two different parts, where first I will give you an introduction on the basic principles of IHPVs, and then I will show you some examples of my own research I'm currently doing in Hanover using our lab. And before I start now with part one, I first want to thank the entire IHPV team in Hanover, current but also former members, since without them, the lab would not be running as it is now, or as it was. So, but before we dive into internally heated pressure vessels, I first want to shortly summarize which techniques and facilities we have currently available to simulate the Earth in experimental petrology. And I want to present them in the order of increasing maximum pressure we can reach, meaning that we can start here with externally heated cold seal pressure vessels. Here are some images, examples, for example, the ones we have in Hanover, or another one which is located at ETH. Then next would already be the internally heated pressure vessels, the IHPVs, which can cover slightly or quite some higher pressures. And here, as example, of course, one of our vessels, or one located at ISTO in Orléans, or here an image of the IHPV from Ville Geotechnik, which will hopefully soon be fully operable in your lab. And in case we would like now to explore even higher pressures, we have to move on to piston cylinder presses. Here, just some example pictures, although they exist in various forms. And if this is still not enough, what you want to do, we have to use multi-anvil presses. Here, for example, the images I stole from your website. So from the multi-anvil presses currently available at FORCE, with Kara here as a reference scale. And in case you would still want to explore higher pressures, we're leaving the field of experimental petrology and rather entering experimental mineral physics, where we are using, or where we can use these diamond anvil cells, although when you have a look at them, they look a little bit less spectacular as the large multi-anvil presses you just saw on the previous slide. So let me summarize this shortly with this Earth transect, where I've shown here just where the general pressure ranges these different facilities cover. So cold seals and internally heated pressure vessels are more or less limited to the crust, where piston cylinders can extend into the upper mantle. multi-anvils into the lower, mid-mantle, and diamond anvil cells far deep down until the core. But let's now zoom in here into crustal conditions, where I have here just put a general cross-section of a continental crust, where we can see that the cold seal pressure vessels are in the end only capable of reproducing upper crustal conditions, but piston cylinders are starting working, let's say, reliably in terms of pressure reproducibility at mid to lower crustal levels, but farther extend down into the mantle. So meaning that IHPVs cover here a crucial pressure range at mid-crustal conditions at around 300 to 600 megapascal, where no other facility currently available is that reliable in terms of pressure reproducibility. So with this, let's shortly summarize or introduce you what is an IHPV, or an internally heated pressure vessel. Well, it is a so-called gas pressure vessel, meaning that we are using argon or a mixture of argon and hydrogen as pressure medium. And although the upper limits of experimental conditions vary quite a lot among the different labs, I'm just showing here now the conditions we are currently capable of reaching in Hannover, which are pressures in the range of 500 to 700 megapascal and temperatures around 1300-ish degrees. And the name internally heated comes from the fact that the furnace, so the heating system itself, is placed inside of the vessel and thus also under pressure during the experiment. And with respect to other experimental facilities covering similar pressure ranges, for example, cold seals or piston cylinders, IHPVs have the huge advantages that we have relatively large sample volumes available. The uncertainties on pressure and temperature are relatively low since we are measuring both parameters directly, and we can maintain relatively wide thermal hotspots in the range of 2 to 4 centimeters. And in case you would now be more interested in some technical details related to IHPVs, I recommend you to have a look at the chapter of John Holloway from 1971 in G.C. Ulmer's book, Research Techniques for High Pressure and High Temperature. Although this book is already quite older, this chapter, the principles are more or less still the same. With this, let's have a general look now at how such an IHPV system works overall. So here a schematic diagram of our IHPVs in Hannover, where we can distinguish three main components of this system, namely a pressurization system, the IHPV system, so the pressure vessel itself, as well as a so-called hydrogen system, which is supplementary, meaning that we can equip the vessel with it, but we don't have to. And this serves to control experimental FO2. I will come back to this in more detail later during this talk. But first, let's start with the pressurization system, which, as the name says, is there to pressurize our experiment, which is consists of an argon bottle, so the gas reservoir, a membrane pump to pre-pressurize the entire system, and then with a so-called intensifier, which we can use, or we use to first compress the vessel to higher pressures and also control pressure automatically during the experiment. And you can imagine the intensifier as a small reservoir which is connected with the vessel during the experiment and equipped with a hydraulic piston which can drive in and out of this volume, thereby decreasing or increasing the real volume, so changing the pressure. So a relatively easy but efficient system. And here just some images from our lab. So here we have the bottle where the gas goes out into the pump, this membrane pump, which is connected with the so-called intensifier you see here, and everything is done with the pressure lines also connected to the so-called pressure vessel. So the key component of our entire system, and thus now the focus of the next part. So in this schematic cross-section, you see the general build-up, how such a vessel looks like, where we have a lot of different parts somehow working together. And first, one of the main components is, of course, here highlighted in red, the autoclave itself, which in the end represents quite a thick-walled steel cylinder, which, well, has to be very thick to maintain the pressure, and is furthermore surrounded by a cooling water coil to maintain its integrity during an experiment, because inside it's getting hot. Speaking of getting hot, the second main component is the so-called furnace system, which is inserted into the vessel from the upper part. And in detail, the furnace looks like this. So we have two main components where we have the real furnace itself, the resistance heating system here at the bottom, or also here on the real image. And on top, we have the so-called closure head. And the heating system is based on a resistant heating principle where we have two molybdenum wire windings acting together to create a relatively wide thermal hotspot. While the closure head, here look for example also this in reality, first serves to seal the vessel in terms of pressure, and secondly provides leading throughs for the power supply, for the electricity, for our furnace to really work, and also now for the furnace side, a small capillary, which is the gas inlet, so where the line where we compress the entire system. And here, just zoom in of how the top of such a closure head, so here it looks like. So we have here these two connection pins, which are these two steel cones, where we are guiding through our entire electricity for the heating. And you see here that they are sealed into the closure head with epoxy resin. And although this looks not very happy anymore, I would say, so relatively burnt, I'm still astonished that such a looking closure head, well, this happens after few experiments and then maintains half a year or so, still pressures of up to 500 megapascal. And this would then just be the interior of the furnace here on top. So the connectors here to these two steel cones, so for the electricity. And then the last main component of our vessel is the so-called sample holder, which in the end just serves us to bring our samples into the hot zone of the furnace. And this is inserted from the lowermost part. And here again, a schematic cross-section or overview of such a sample holder, where we can distinguish three different zones or parts. So we have again a so-called closure head, which serves to get a variety of signals in and out of the vessel with these different cones. Then we have a cold zone where we quench our experiments, and we have the hot zone where the samples are located in the thermal hotspot of the furnace. Here, just also the comparison, the sketch, and the real image, how this looks like. So let's start with going through these different zones, and I want to start at the bottom with the closure head. So the same principle, we have this steel plug, and this time we have a variety of different, we call them cones, made of steel, which we need to get distinctive signals inside of the vessel, for example, thermocouple readings or the Shaw membrane signals out of the vessel. And we have normally attached there two thermocouple cones, one quench cone, which looks in detail like this, which we need to quench our experiments, and then this supplementary Shaw membrane cone, which is part of the hydrogen system. And these cones are then just sealed into the closure head again with epoxy resin. And it's holding pressure. I'm still astonished after all these years in Hanover. Then before we move to the uppermost two parts, here just an overview image showing you all parts we now need to build the remaining sample holder. So you see there are quite a lot of different small parts which are involved there. And every one of these has its own purpose. And in the cold zone, so located above the closure head, this has first the purpose of providing with this copper block a base for the cold zone, so for the quenching. So when the capsule falls here in the inside on this copper, it will cool quite rapidly, thereby allowing quite fast quenching rates. And secondly, the cold zone is also there to allow us to connect the incoming wirings from the closure head with the uppermost or upper-lying thermocouples, quench lines, etc. So it's mainly the connection piece of the electrical signals. Which brings me then already to the hot zone, where our samples are located and where we are measuring the experimental run conditions, which therefore we have a shell membrane for the FO2 and normally four thermocouples to monitor and control temperature. And the capsule is then suspended in a platinum wire here in the hot zone of the furnace. By the way, also here how this looks in reality. And one of these two quench lines is then via the cold zone and the closure head connected to the outside of our vessel. And when we apply there an electric power source and a short pulse, we will create a shortcut in our system, thereby fusing this thin platinum wire up here, allowing the capsule to fall down to the cold zone, resulting in cooling rates exceeding 100 degrees Celsius per second. So relatively fast. And you see now, when you have a look at the sketch or the image, that the sample volume we have available in IHPVs is relatively large, meaning that we can either run very large capsules in one go or packages of up to, I think the maximum I did, 8 individual capsules. And here just some images of capsule packages I ran so far in our vessels. And this means now, with this large sample volume, that we have some crucial advantages of IHPVs. For example, they allow us to synthesize quite a lot of material in one go, just in one run. So, for example, if you want to synthesize something like a standard, which we also want to distribute into the community, the IHPV is quite a good facility you can use for this. And secondly, due to this large volume, this allows us also to run quite some systematic experimental studies. So imagine, for example, that you want to have a look at the effect of water on phase equilibria. So you can take one bulk starting material composition and prepare capsules with up to 8 different water contents, which you then can, as such a package, run in only one experimental run at the same temperature and pressure, and this with just running the IHPV bonds, you can already create quite an extensive data set. So if you want to do systematic studies, I think also IHPVs are very, very useful tools. And with this, let's now have a look at the so-called hydrogen system, which is, as I said, supplementary, meaning the vessel runs without it, but can be equipped with it. And this mainly serves us to control and also monitor the experimental FO2 conditions, and thereby consists of a hydrogen bottle, which is connected here to the vessel, allowing us to put some hydrogen into the vessel itself, and a shell membrane which is located inside of the vessel and then via this outgoing line connected to a pressure transducer and a vacuum pump. And here an image of one of our vessels which is equipped with this hydrogen system. So no sample holder is currently loaded here, but that would then go in here, and the shell membrane will be connected to this hydrogen outlet line and the pressure transducer. And speaking of FO2, here let's now shortly discuss how we can control, in fact, oxygen fugacity in IHPVs. And generally here, the gas, which we use for pressurization, as well as the vessel, they will impose a certain hydrogen fugacity in the vessel, which will result in a specific oxygen fugacity in our experiment. Meaning when we use pure argon as pressurizing gas, we also call this intrinsic in Hanover, we will get an FO2 in the experiment of around NNO plus 2.3, so relatively oxidizing. And now, using our hydrogen system I just presented on the previous slides, we can add some hydrogen to this argon and thereby lower its imposed FO2 conditions, where currently we are capable of reaching up to roughly conditions of NO-1. More reducing, I would not go in our vessels currently. And for the FO2 buffering now, we're taking advantage of the principle that metal capsules are generally permeable to hydrogen, meaning that the fugacity of hydrogen in the vessel and the capsule, they will equilibrate during the experiment, as shown here in this sketch, where the hydrogen entering the capsule will react with the water present there via the water dissociation reaction, and we can formulate this then, or we can then try to calculate the FO2 via the equilibrium constant of this reaction, resulting in that the FO2 in our experiments corresponds to 2 times the logarithm of the water activity inside of the capsule minus this factor, which in terms of simplicity, I will not just call the intrinsic FO2 vessel imposed, or FO2 imposed by the vessel. And this equation here with this term means that in case the water activity in our experiment is below 1, the FO2 we will get in that will be lower than the imposed value. And as a consequence, the buffered FO2 conditions in our experiments will always depend on the water activity of each individual run, meaning that the oxygen fugacity we impose with the vessel will only correspond to the FO2 inside of the capsule at water saturation. And this is a very important principle and also applies to many other FO2 buffering techniques we're currently using in experimental petrology. So this is how the buffering works, but how can we now monitor if the addition of hydrogen, or if we added the right amount of hydrogen to reach the FO2 conditions we wanted? Well, one first possibility for this are the usage of so-called Shaw membranes, which you see here the general setup, how they are built, or here some images of them in reality. And they are based on, in terms of functioning, exactly the same principle as before the FO2 buffering, where the noble metals are permeable to hydrogen, meaning that the partial pressure of hydrogen we can measure inside of the Shaw membrane via the connected transducer at the outside of the vessel will equilibrate with the hydrogen partial pressure inside of the vessel. Meaning that when we measure this hydrogen pressure, we can directly monitor the FO2 imposed by our vessel on our capsules. However, there are some issues with Shaw membranes. For example, their equilibration here in hydrogen partial pressure can take quite a while. And it's very hard to judge at which stage now we reached equilibrium or not. Then they also pose a risk for vessel failure, since you have to imagine this small platinum tube used here, welded on top, is the only barrier or seal for the entire pressure inside of the vessel. So meaning if this cracks, we will just empty the vessel more or less in one go, and this happened already from time to time in our lab. And a further complication is that such a Shaw membrane up here in these porous parts can get clogged with time, resulting in misleading readings. But how can we now tell just directly that the Shaw membrane is not working anymore? So also hard to judge. And due to these unfortunate limitations, we currently run our vessels in Hannover without Shaw membranes. But if this does not work, can we still try to monitor now oxygen fugacity conditions in the experiments? Yes, we can, because there is another principle of so-called redox sensors, which are currently employing more and more. And it is based on the principle of contaminating a well-calibrated and parameterized FO2 buffer equilibrium with an additional component. And I want to exemplify now at the example of the cobalt oxide FO2 equilibrium, which is in this plot here is located at this line. And when we now add, for example, palladium metal or magnesium oxide to this buffer equilibrium, so we contaminate it, these additional components will react with the buffer assemblage to either form an alloy or solid solution, where the composition of these two new compounds will directly be or related to the imposed FO2 conditions. So meaning if we measure the composition of such a cobalt-palladium alloy, we can back calculate the FO2 conditions at which this one formed. And when you have a look at this plot, you see that here the cobalt-palladium system more or less covers the entire FO2 range, which is most important for magmatic processes, meaning that we're currently using this system to monitor the FO2 conditions in our vessels. And this is what we just did in a recent study. Or wait, before I go to that, first I want to show you how these sensors look like. So we have normally just a noble metal capsule where we have such a cobalt oxide, palladium pellet, just made of powder, enclosed in zirconia powder, and added some water, which we need to allow the sensor to adapt to changing FO2 conditions. And the zirconia powder is there to protect the sensor from any alloying with the noble metal from the outside. And now let's come to what we did recently. So you can monitor now your FO2 conditions by just adding such a redox sensor capsule to your experiments. And this we did in a recent study where I think few of the audience or some of the audience are also here, where people which were involved, where we were able to first measure the intrinsic FO2 conditions of our argon-only vessels, where we obtained FO2 of around NNO plus 2.3. And it also allowed us to check how well we could reproduce the FO2 conditions with the argon-hydrogen mixtures in these vessels. And you see here that this worked quite well. And I think this shows that our general approach of buffering FO2 in our IHPVs is working. However, in case you want to run some studies where FO2 is absolutely crucial, I still recommend you to always also monitor the FO2 using these sensor capsules. And with this, let me show you now some few images about daily IHPV lab life. So for example, we use in our IHPVs quite a lot of ceramic parts, which are often quite fragile, so we're often dealing with broken parts and some repairs. Then the furnaces, they're homemade, and they can from time to time do strange and crazy things, like for example here, which can screw up your entire experiments. For example, here a molten capsule package where we have some basaltic glass and a little bit bulb of gold. And one of the most most often occurring issues we're dealing are leaking sample holders. So just that one of the cones is releasing a little bit of gas, not tight anymore. And this is exemplified here with our argon sniffing tool, that there is some argon coming out here. And this can even get more severe, where, for example, in this case, an entire cone shut out, thereby ripping off all the sample hole or all the thermocouple connections down here and releasing the pressure of the vessel more or less immediately in one go. And just recently, we had also a problem that a sample holder got stuck inside of the vessel. And what you see here is the part which had just ripped off while trying to get it out. Well, some illustrations showing how it could go in the IHPV. However, often everything works quite nicely. So in summary, I hope in this first part I could show you a little bit how such IHPVs work in general and how we can monitor and control the FO2 conditions in these facilities. And I hope I could convince you of the advantages of IHPVs over other facilities, such as the large sample volume, the precise control of pressure and temperature, the wide thermal hotspot, and the near instantaneous quenching rates we can achieve. And I hope I could, with this, also motivate you to further incorporate for your future research projects IHPVs. And I wish you already a lot of fun with your own facilities, with your own IHPV, and hope that it will be run or will be capable of being fully operatable soon. But for the remaining time now, let me shortly show you what type of research we can effectively do with IHPVs. So let's move on to the second part, where I want to show you how we can quantify phase equilibria and silicate mineral stability fields in calc-alkaline basaltic systems using internally heated pressure vessels. But why should we care now about calc-alkaline systems? Well, calc-alkaline magmatism, or more than 75% of currently active volcanoes on our planet, are fed by calc-alkaline magmas, where many of them are also located in quite close proximity to highly populated areas. And on top of that, calc-alkaline explosion or eruptions are often quite hazardous and explosive. Since many of the most forceful eruptions recorded in human history were of a calc-alkaline origin. For example, Krakatau, Tambora, or Pinatubo, and although less globally hazardous, still the Mount St. Helens eruption in 1980. And in order now to better understand these systems, how these volcanoes work, and trying to reconstruct magmatic processes, we have currently in petrology quite a lot of tools available trying to estimate crystallization conditions from the natural rock record, for example, to try to formulate such a polybaric differentiation model for arc magmas. And these tools include, for example, thermobarometry, where we can try to calculate crystallization conditions, so pressure, temperature, of using some calibrated mineral melt or mineral only equilibria. So some algorithms with, although their general applicability to natural rocks or some systems is currently highly debated in the community. Alternatively, we can also try to simulate the crystallization of a melt using some thermodynamic models, such as melts or comagmat. However, also these are currently showing quite a limited performance in water-bearing systems, so for example, calc-alkaline magmas. And the last thing we can do, or another thing, is we can run some experiments, for example, running some phase equilibrium studies, trying to simulate or reproduce some natural observations, where these experiments can also serve as crucial input data to further improve the two previously mentioned petrological tools. So thus, in this project, we want to experimentally quantify systematic variations of magmatic phase equilibria with a focus on near liquidus phase relations in mafic calc-alkaline magmas, meaning that we were mainly interested in the stability fields of olivine, ortho and clinopyroxene and plagioclase. Where we know that these are affected by various parameters, including temperature, pressure, bulk system composition, water content, or oxygen fugacity, where in this study we were mainly focusing on these four first mentioned one. And for the effect of pressure, this is, for example, nicely illustrated here in this phase diagram, where when we decompress along this arrow, we see that various different mineral stability curves are crossed. And for this project now, to keep the amount of experimental work at a doable level, we decided to run or to use systems or study systems which have already been investigated experimentally to some extent in the past, so we can just extend these data sets to upper mid-crustal conditions. And this resulted in the selection of two relatively famous, I would call them starting materials. One, a basalt from the Adamello, from northern Italy, where I myself and other people from ETH already worked quite a lot on. And the second composition is a basalt from Mount Rainier in the Cascades, where Danica Blatter and Tom Sisson already spent quite some time with. And what is now less surprisingly, of course, in the frame of this talk, is that I did for this project then some experiments in our IHPVs. I ran 200 megapascal experiments on both compositions at temperatures of around 1000 to 1200 degrees, with 3 different water contents for each starting material to account or to investigate the effect of water on phase equilibria. And for the 400 I additionally did some 400 megapascal runs on the Adamello compositions, where I just expanded the range of water contents to higher levels to account for the higher solubility of water at higher pressures. And for this project, I used mainly these two IHPVs we have currently available in our lab. So let's have a look now at some of my data. But first, I want to show you the effect of water on phase equilibria, here first for the Cascades basalt at 200 megapascal, where in this temperature, meltwater phase diagram, each hexagon corresponds to an experiment I did, where the smaller colored triangles indicate if the corresponding mineral phase was stable or not at that conditions. So colored means stable. And the meltwater contents, by the way, were here established either by Raman spectroscopy, or if this data is not yet available, we're currently in the progress of getting them, measured, calculated by mass balance. And overall, we can see here a general destabilizing effect of water on silicates, while apparently spinel stability, here exemplified with magnetite, is not affected by the meltwater content. And if you look now in more detail, we can see that the plagioclase and clinopyroxene saturation curves, they cross over here, roughly at intermediate water contents, that offer pyroxene stability is limited to lower temperatures and lower water, and that amphibole saturation was only reached at high water and low temperatures. And in the next step, we can compare this now to the 200 megapascal data on the Adamello composition, where the general pattern looks relatively similar to the cascades. However, we can observe an enhanced CPX stability and, more crucially, the absence of amphibole at low temperature conditions. So here we clearly can identify the effect of bulk system composition on phase equilibria. And we can also have a look shortly at the 400 megapascal data for the Adamello, so where we see a stabilization of clinopyroxene, an overall stabilization of amphibole, now it is there, before it was not, and a general destabilization of plagioclase with increasing pressure, resulting in that even the highest water series here are not saturating in plagioclase upon progressive crystallization. So here we see a distinct pressure effect on phase equilibria. And this all then can, of course, also be translated into the liquid line of descent, so the chemical evolution trend of the residual liquids. Here first only shown in green for the cascades at 200 megapascal and the Adamello composition at the same pressure, where interestingly we can not really see a distinct influence on the starting material composition on the liquid line of descent. So they both define one single trajectory, and moreover, it's also interesting to see that variations in melt or in water contents, here in bulk water contents, seem not to affect the LLD itself. So they're all lying still on the same trajectory. However, such a change in water content will only result in a relative shift on the liquid line of descent. So, for example, an Adamello run with a high water content might plot up here, so not a lot of crystallization was going on, but at the same temperature and pressure, a low water run might already be down here, so distinctly more differentiated, just due to a higher crystallization degree. And when we add now in these reddish and yellowish colors the 400 megapascal data for the Adamello, we see a shift of the liquid line of descent towards lower CPX components, thereby nicely illustrating the well-known by now effect of pressure on the olivine CPX contactic, which, as shown here in this schematic diagram, where an increase in pressure brings down this reaction or this contactic curve towards lower CPX components. So this is now all very, very nice. So I can describe my experimental data, but as you might remember at the beginning of the second part, I told you that the idea here was also that we try now to quantify phase equilibria. And for this, the first idea I had was that I wanted to try to formulate some mineral saturation models, so an algorithm which allows you to predict the saturation temperature, so the highest temperature of crystallization of a mineral in a magma as a function of various parameters, where I'm currently accounting for trying to incorporate pressure, bulk water content, the bulk system composition, and the oxygen fugacity. Where for the bulk system composition, I had the idea to account for this using a normative mineralogy. So the same you already saw on the previous slide, where my idea, a composition that has, for example, a higher clinopyroxene component, such as the adamello here, should theoretically thus also saturate earlier in the phase upon crystallization or upon cooling, and thus being much more indicative, such a normative mineralogy, than just a simple element or oxide ratio. And so far for these mineral saturation models, I was focusing my efforts on clinopyroxene and plagioclase, and let's now shortly have a look at my first attempts. So first, for clinopyroxene here, I did a simple linear multi-component regression on my experimental data, which then gave me this saturation model equation. And in this plot, I show you the predicted saturation temperature using this equation plotted against the experimental saturation temperature based on my observations from the experiments. And here you see already that this first quite simple model already seems to work quite well. So we have a relatively low error of estimate and a high R-square. However, now from literature we know that water contents tend rather than linearly to affect mineral stabilities non-linearly. And this is what I then accounted for in a new version of this model. So I added this exponential term here for water, and in fact the model slightly improved, so the errors became slightly lower and the R-square is now higher. So this seems already to work quite well. Let's now have shortly a look at plagioclase, shown here, where this time I could not observe for my linear or generally an effect of bulk system composition and FO2 on plagioclase saturation. But here, which is quite remarkable, I think, is that although I tried again with a linear and a non-linear water term, this time both models are performing equally well. So the errors and the R-squares are more or less identical. And it seems like apparently water contents seem not to affect plagioclase saturation in a non-linear way. And to make these models a little bit more applicable to a more general data set or general rocks with observing nature, I tried to incorporate further literature data, so other experimental studies, to improve or to make the fit more general. So I extended these with this literature data, and here you see my first attempts, just my first result. This is all preliminary work. And of course, now the errors slightly increased, but I think the R-squares or the general fit looks still promising, and it's definitely worth to spend a little bit more time with this in the near future. And before I now come already to the end, I first want to show you what we can also use now, this entire data set of my experiments I obtained, for what we can use it. Namely, we can, for example, use it to try to test the general performance of some thermobarometric algorithms and their general applicability to natural or especially now mafic calc-alkaline rocks. And here I want to shortly focus just on the hot topic of clinopyroxene melt thermobarometry, where what I did here is just that I took my experimental melt and clinopyroxene compositions and then use them to calculate with all these models the effective or the predicted temperature and pressure of crystallization. And by comparing them now, of course, to the measured and known experimental conditions, I can tell or judge a little bit how well these models are working. And here I'm only showing you now the results for the relatively recent Neve and Portirka algorithm, which was among the best performing ones I explored. And for temperature, I think we can see a more or less okay-ish result. So the temperature thermometer seems to work, so we can use it. And an interesting thing here is that several of my clinopyroxenes, they show some sector zonation in alumina. And although both sectors seem to more or less perform equally well for the temperature. So it seems that I cannot currently use such models or formulations to make more statements about which of these two sectors is now really the true equilibrium composition, or if even one of them is in equilibrium. Well, but if you have a look now at pressure, the story looks quite different. So for example, when we have a look at my 400 megapascal experimental clinopyroxenes, we see that the calculated pressures predicted by this barometer more or less range from 900 to almost 0 megapascal, meaning they cover the entire crustal column. And this then leads, or for me, means that currently we cannot use such thermobarometers or barometers based on CPX or CPX melt to make any reliable statements regarding a transcrustal magmatic system. So potentially, I recommend you to keep this in mind when you next apply such barometers to your natural samples. And with this, we've reached now already the second part of my talk, and I hope I could show you how we can use IHPVs to run a systematic study, for example, on the effect of pressure or water content and bulk composition on phase equilibria in mafic calc-alkaline magmas. And that we can also use in this data to predict or trying to predict phase equilibria by formulating some mineral saturation models. And the data sets can also be used to test commonly used CPX-based thermobarometers for their general behavior or performance, where we saw that temperatures are occasionally reproduced, the results are reasonable, while pressures are quite, in fact, certainly not. And for the near future, I would like, of course, to refine these mineral saturation models and also start testing some more plagioclase-based barometric thermometric equations. Already some attempts you see over here. And we had once an ultimate goal of trying to formulate a new thermodynamically based plagioclase liquid equilibrium model for hydrous systems. And although this is less certain if we will still do this, there was the idea that we could use our new data set now in combination with recent literature data to recalibrate some of the currently existing CPX thermobarometric models. And with this, I thank you for your attention, and I'm happy to take questions.
Thanks so much, Felix. That was a great primer for the IHPV, and your experimental work is really interesting. Oh, this is a great photograph, too, of the zones on your crystals.
This one?
Yeah.
Yeah, that's on my PhD thesis in the end.
If anyone has questions, you can type it in the Q&A and I'll read it out, or you can raise your hand. Okay, so Max Collinet, thanks for attending. He says, thank you, Felix, for the great talk. Did you use the cobalt palladium buffer in the experiments you presented in part 2? And does it work well, including at low pressure, about 200 MPa and under?
Well, I did not use them for these experiments. Because, well, they were all done, what I showed you in terms of these experiments, in the argon-only vessels. So where we only use the argon to monitor or as a pressure medium. So we have no direct control, let's say, on the oxygen viscosity. It is directly controlled just by the argon itself, and which we then constrained with this other study where we measured the intrinsic FO2 at more or less similar run conditions to be at NNO plus 2.3. And it was the same vessel which I used, so I assume that it should be the same. Because all these sensors you saw, they were also done over, I think, a period of 1 year. So we did not observe something like an altering or change of the vessel buffering capabilities. And regarding the applicability of the sensors, they were, in fact, I think, calibrated at 200 megapascal originally by Taylor et al. 1992. And I even, in my thesis, I extended this calibration equation also by a pressure term. So just the equation of state of the entire system. So making it theoretically applicable to higher and lower pressures. Although I think the effect is relatively small. So in the range of 0.2 to 0.5 log units. So not extensive, the effect of pressure.
That makes sense. Thank you. And next, Rick Hervig asks, have you observed contamination of noble metal capsules with other elements such as lithium or boron?
I have not, not in my experiments. Although I have to admit that lithium and boron we did not analyze. We only did microprobes, so we only more or less the major elements. But at least from my experience, from my PhD in ETH, where we also use cold seal pressure vessels, I never saw something like that. since, yes, I lasered quite some of the glasses there for traces, and the only contamination I mainly saw was tungsten via the needle of the welder. So I had heated glasses with up to 1,000 or 2,000 ppm of tungsten.
Rick says, as a follow-up, we have seen up to weight percent levels of boron and lithium in experimental glasses that we count to contamination from noble metal capsules. So might be something interesting to look into if you can't explain something's happening in your experiments.
No, never heard of that, but sounds interesting. I might have a look at when we plan the next time to do some laser measurements on some experiments. I will keep that in mind. Thanks.
Great. Do we have any other questions? Okay, so let's thank our speaker again, Felix Marxer. Thank you again.
Thank you for the invitation.
I know it's late where you are, so we really appreciate it.
Thank you.